And ladies and gentlemen, welcome back. It's Mr. Simpkins here in the Simpkins Physics Corner with some AP blended energy practice problems. So we've been talking about conservation of energy, or at least that's what we're getting into now. The idea that energy is not created or destroyed, but rather changes form, not amount, when work is done. Because we know that when work is done, energy changes. So let's take a look at an example like this with some blended energy. We have an automobile traveling, as you see in the diagram, and it's up on a hill, so anytime you can fall, you're going to have gravitational potential energy, and it is also moving, so we have kinetic energy. And then it says the car coasts down the hill and then continues coasting up the other side until it comes to rest. Ignoring frictional forces and air resistance, it's the value of h, the highest point the car reaches above the bottom of the hill. Now, when we get to this point, we say it coasts to a stop, so at the end, we're only going to have potential energy. There's no springs compressed, and we're not moving. And what does that mean? Well, the idea here is that the total energy before or at one point in our system, if there are no non-conservative forces doing work, which in this case there aren't, the total energy at the beginning of our scenario has to be equal to the total energy at the end of the scenario. Well, we have to ask ourselves, what kinds of energy do we have? This car initially has UG, but it also has K, and I'll call that UGI just to differentiate it between the final potential, gravitational potential energy we have. And so we go to our equation sheet. We see mg delta y initial plus 1/2 mv squared equals mg delta y final. All right. And these equations come from your equation sheet. So if you look for K, big K is 1/2 mv squared. That's kinetic energy. Mg delta y is the energy associated with gravitational potential. Now, you may notice that each of these terms has an m. So the mass actually cancels out in all the terms. If you're wondering about the math, if you look at the left side, you could factor out m and then divide both sides by m, right? But because every term has an m, you can cancel it. You can't cancel the mass if we have springs involved, which we'll see in a little bit, because not every term has an m if you're using the spring equation. But let's continue with this one. So we have g delta y initial plus 1/2 v squared equals g delta y final. Okay, well, let's go ahead and plug some things in. We're doing math, so we're going to be precise and use 9.8 meters per second squared. That's going to be our g. Our delta y here is 5.4 meters. And then we're going to add 1/2 v squared, 26.2 meters per second. And we're going to square that whole deal. Excuse me. And that's going to be equal to 9.8 times delta y. So I'm going to pause and do a little calculator magic. Bam! And we got the calculator magic going on. You can pause to take a look at those steps. Just plugging and chugging. We notice that our final height is 40 meters, which makes a lot of sense if you think about this. You're like, Mr. Simpkins, we only started at 5 meters. Yeah, but look how hot we were going. We were moving pretty fast. All right? And so because we were moving so fast, it's going to give us a lot of energy, a lot of kinetic energy in this case, to carry us up that hill to a point of higher potential. That point is 40.4 meters. So there's a first little example. Big picture, though. At the beginning of the problem, our total energy has to be equal to the total energy at the end of the problem. In this particular case, at the beginning we had both potential and kinetic, and at the end we had just potential. Let's look at another one. We have a pebble shot straight up with a catapult whose spring constant, oh dear, is 320 newtons per meter. The catapult is initially stretched by 0.3 meters. How high above the starting point does the pebble fly? Okay, so we have a little spring cannon here. So let me go here and say, here we go. We got a little spring, and we'll put a little pebble on top there. Look at my amazing art skills here. And that guy is going to shoot there how high above the starting point. So we're going to assume that the starting point, in fact, we're not going to assume, we're going to define our starting point as right when it comes out of the cannon. All right, because as it's in the cannon, it is going to be shooting. This is going to get a little tricky, but we'll go ahead and figure it out anyway. It says, oh no, you know what? That's not our starting point. Our starting point is when the spring is all the way compressed. So that's where we originally start, right? Then we're going to go, and we're going to load the cannon so the spring is really, really tight, and then it's going to go, pew, it's going to shoot up to some tall height there. All right, so the reason I didn't pick this point number 1 here as our starting point is because there we're above the ground and our spring is not compressed, right? So I'm actually going to pick the point where we are at our lowest height and our spring is compressed. And why do we choose to do that? Because then we only have spring potential energy at the beginning of our problem, and at the apex, we only have potential energy. And we have potential energy relative to the height of that starting point. So let's see how this works. We know conservation of energy says that the total energy at the beginning of a situation must be equal to the total energy at the end of a situation. At the beginning of this situation, we have US, or spring potential, and at the end, we have gravitational potential. So if we use our equation sheet, 1/2 kx squared equals mg delta y, and this might be slightly new for you. K is the spring constant. So this spring constant here, that's defined as K. And x is the distance that the spring is stretched or compressed. So in this case, it says it is stretched by this much. So let's go ahead and plug some stuff in. We got 1/2 times 320 newtons per meter. Our x, our compression, or in this case, our stretchy distance is 0.3 meters. That's got to get squared, and then that's going to set that equal to. Now here the masses don't cancel, you see, right? Because we have kx squared on one side. So don't get all mass cancel happy here. Some people like to just smash the masses, and you can't always do that. So m times g times delta y. That's, of course, going to be our final answer. I'm going to pause for some calculator magic. You can pause right now and do the math. Check in a second. Calculator magic, and we got our height that we go to is 26.7. That is hot. I guess we have a very stiff spring and a very small pebble, because that is very, very high. All right, but that's how the math would work out. We have the initial spring energy is equal to the final gravitational potential energy, and we set them equal to each other. So not too bad for that one. Let's take a look at this guy. It says a block is released from rest and allowed to slide down a frictionless surface into a spring. The far end of the spring is attached to a wall. The initial height of the block is 0.5 meters above our floor. So I'll just write that right there. And it's a 2 kilogram. Oops, sorry. It's a 2 kilogram block. And we got a spring constant of 450 newtons per meter. That's going to be equal to K. It says, what's the block's speed when it is at a height of 0.25? Oh, so we got to figure it out right here. And then it says, how far is the spring compressed? And the spring sends the block back to the left. How high does the block rise? Lots of good details in this one. So let's break it down step by step. I'm going to define points A as the top point here, point B as halfway down the ramp, and point C as when the spring is all the way squished when our crate hits it right there. So we're going to define those points. And the reason we have to do that is because we know that the total energy at all of those points must be equal. So whatever we have going on at A, the total energy has to be equal to the total energy we have going on at point B. So let's go ahead and do that. At point A, we only have UG. We only have gravitational potential because it says we are released from rest. But at point B, we have both gravitational potential and kinetic energy because we're on our way down the ramp. And so when the question says, what's the block's speed, right? Speed is associated with kinetic energy. So let's go ahead and bust out these equations here. We got mg delta y at the beginning is going to be equal to mg delta y sometime later. I'll write that as initial and final. And then I'll do plus 1/2 mv squared. Ha-ha! Everything has an m, which is beautiful. So we can cancel out the mass since every single term has it. Remember, you can't do it unless every single term has it. And so we have g delta y initial equals g delta y final plus 1/2 v squared. And you may start to notice a pattern in these problems. That's because there is one. But let's go ahead and do a little algebra here. We got 9.8 meters per second squared times 0.5. And I'm going to subtract this term from both sides. So I'm going to say minus 9.8 meters per second squared times 0.25. And that's going to be equal to 1/2 v squared. Okay, so let's do some calculator magic here. I'm going to pause for the magic. And calculator magic, boom, we go ahead. We started with the total energy at point A, which is UG, and then at point B, it was UG plus K, potential and kinetic. We went ahead and expanded those equations, got all the way down to the bottom, had to take the square root, and we find the speed at point B. All right, let's continue for the next part of the question. How far is the spring compressed? So this is where you need to know your definitions. When it's saying that, what it's asking you to solve for is x, particularly x in the 1/2 kx squared equation. Now, I could set all of the energy at point B equal to all of the energy at point C, but B has two kinds of energy. Why would you do that to yourself? Right? I'm going to pick an easy choice. I'm going to set the energy at A equal to the energy at C, because the total energy of the system has to remain the same unless there's work being done by non-conservative forces such as friction. In this case, we're frictionless, so this is a safe thing to do. So at point A, we only have UG, and at point C, we only have US, the potential energy stored in the spring. And so mg delta y equals 1/2 kx squared. And the question is asking us to solve for the x. So I'm actually just going to bring this up here. I'm going to do a little algebra here. See if you can follow me. 2 mg delta y, I multiplied both sides by 2 to get rid of the 1/2. And then we'd have to divide both sides by k. And then we'd have to take the square root to get it equal to x. Now you'll notice on the right side of this slide, I solved everything plugging in the numbers pretty quickly. One of my old physics teachers used to tell me, hey, always do it all the way in variables until you get to the end, if possible. And I always thought that was dumb advice. And then I did more physics and I realized it was really good advice. So if you can, especially because the AP exam often asks you to derive an expression, right? Try to stick to the variables until the very end. So this is how you would derive your expression in terms of physical constants, G, and variables M, Y, and K to solve for X. That's what the problem would actually sound like. And so now I have to do some calculator magic. So I'm gonna pause, plug, and report back. Bada bam, Mr. Slam, 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 and we got the X compression is 0.209 meters. Cool. So these are some samples of what you're going to see what we call blended energy problems. All right, later in the week, I'm going to give you an insane problem where we have stuff going on all over the place. Not this one, just ignore the words on that page. This is not even right here. But like, let's say I said, okay, I have a spring compressed at the top of a cliff, and that cliff goes down into a loop-de-loop, which then so happens to have friction, and then you get to the end and there's another spring at the end there. All right, this seems insane, but you could do it, right? Because up here, when you compress your spring, you'd have US and you'd have UG, right? Because you have some height, so you have gravitational potential and you have a spring. And then I could say, all right, over here, how fast is this thing going, right? Well, you would have some height associated with this, so we would have UG and we would also have K. So do you see how if I told you how high we were and how far the spring was compressed over here, you could set that equal to how high we are and how fast we're going over here, or you could find out how fast we're going over there. Then what about this? Okay, so let's say you have 1,000 total joules coming in right here, and then you hit this friction place. Well, we know that when work is done by the force of friction, energy changes. So if I gave you the mu, right, and you knew the mass of the object, you could do the whole normal force equals the force of gravity thing. You could, if I gave you that distance, you could solve for how much energy was dissipated or lost in non-conservative work, and maybe only 800 joules comes out the other side. So this is the big term, long-term picture of what we're thinking. You can do this for any two places. You can set the total energy at one place equal to the total energy at the other place, and even if there is a friction, something like friction doing non-conservative work to remove energy from the system as we've defined it, then you can still account for that. You would just have to take that energy away as you hit those places. All right, so stay tuned for the rest of the week. Check out the conservation of energy asynchronous 2 practice problems if you want to flex your muscles a little bit more on these. Until next time, this is Mr. Simpkins in the Simpkins Physics Corner.